Hey everyone, I've decided to create a short series of videos on ECG signal preprocessing in Python, because I feel like there aren't many resources on YouTube on this topic, so I kinda wanted to fill that gap myself. Over on the left, you can see an overview of the series. First, we'll start with loading ECG data in Python. Then we'll move on to inspecting the data, which is very important when working with any kind of dataset. After that, we'll dive into filtering the data. And finally, we'll wrap up with feature extraction from the ECG signal. So without further ado, let's jump right in. So I would like us to start with loading our data and inspecting our ECG signal. It can be done in many different ways, but we'll just stick with plotting the signal and inspecting the shape of the data. So we will need these two functions, butter and I'll filter for our future bandpass filter. WFDB to load and read our signal. Matplotlib is to plot our signals, and of course NumPy. Typo, sorry. All right. I will leave a link in the description for this data set. It is from the PhysioNet website, but if you have your own data set, it's totally fine, but just keep in mind that different data sets are being loaded differently. So in our case, we can use the WFDB library to do so. Our D record to load the signal. And here we will read our record variable, our signal. All right, now let's take a look at our signal and plot it and see what it looks like. So we'll plot our signal and we'll give it black color. All right, so this doesn't really look like an ECG signal. It looks like it's messed up. And the reason for that is because ECG recordings have 12 leads. And right now we are having 12 leads overlapping each other and making this mess. So what we need to do is just select only one lead. And to prove that we have 12 leads, we can actually print the shape of our data. Okay, so you can see 1000. The first number is the number of data points in each lead, and 12 is the number of leads. So we can just select index 0. That'll be our first lead. Okay, now it looks better. We can even just zoom in and plot the data points from 0 to 500, let's say. Okay, now it looks better. All right, it's time to make our bandpass filter function. And it'll take a few parameters. It'll have our signal, low cut, high cut, sampling rate, and filter order. We'll use the second order. Now we need to define our Nyquist frequency. So what Nyquist frequency does, it prevents our signal from being distorted. It just cuts our frequency in half. So for example, if our frequency is 100, it'll be 50 hertz. So our frequency is 500 hertz multiplied by 0.5 will give us 50 hertz. Then we'll need to find our low and high. Low our low cut parameter divided by Nyquist. It'll just normalize the value that we will have. So for example, our low cut frequency will be 0.5 hertz. That means that what about low cut and high cut? So low cut and high cut are two thresholds for frequencies that are in a higher spectrum and frequencies that are in the lower spectrum. So everything above high cut will be filtered out, and everything below low cut will be filtered out too. So let's say our low cut is 0.5 hertz, and our Nyquist frequency is 50 hertz. And it will give us 0.01 hertz. This is the normalized value that will be used during the filtering process. Okay. Now we need to define our coefficients. We can make B and A, which will take the normalized value from low and high. Butter function. We'll have our order, just order 2, and our low and high values. And B type equals band, means that we're using bandpass filter. And finally, we use our filter function, B, A, and signal. Okay. Now let's define our low cut and high cut. And our sampling rate, which is 100 in our case. So these are just the values that we usually use with low cut and high cut, but feel free to experiment with different numbers and see how it affects your signal. Okay, now we can try to apply our filter to our signal. Signal, low cut, high cut, and finally our sampling rate. Okay, done. Now let's try to plot the signal and see if it's different from our previous plot. So I'll do is just change this to filtered signal. Alright, so now we can see that it looks the same, nothing happened. And it took me some time to find out why. So it turns out, because our data is two-dimensional, remember we plotted the shape of our data? It was 1012, so it was two-dimensional data. And when we use when we apply our filter onto two-dimensional data, it doesn't work as expected. So the solution that I found is that we can make our data one-dimensional, apply the filter, and then make it return to its original state, which is two-dimensional data. If you have any other solutions, please feel free to write down in the comments and let me know what you think about it. So let's proceed with that. So the first step is to flatten our data, is to make it just a 1D array. Okay, so we can signal. All right, let's try to see if it worked. Nice. We can see 12,000. So it just won the array now. And now we can apply our filter to our one-dimensional data. Okay. Okay. And now, after the filter has been applied, we can give it back its original state. So reshaped. Filtered signal reshape. So 1,000 points and 12 leads. Okay, let's try and see if it worked. All right, great. We can see the difference now. For example, these P peaks are lower now, and there is less noise, so the signal is kind of smoothed out a little bit, and that makes our signal ready for the next preprocessing step, or for feature extraction, which we will do in the next video. Yeah, hit that like button if you find this video useful for you and if you learned anything from it. I'll probably I will attach this code to my GitHub repository, and make sure to check out my ECG classification machine learning deep learning project, which is also in my GitHub repository, if you want to take it a step further than now and actually preprocess the signal, label the signals, and develop or experiment with different deep learning machine learning algorithms for the final classification. That means that'll be very interesting for you. All right, so I'll see you next time. See you in the next video.